From the creation of ice ages to the effects of global warming, the Earth's climate is a roller coaster of change. And our next great discovery helped put it all into perspective.
For centuries, people believed that the Earth was shaped by catastrophes, like the biblical flood. But in the early 1800s, an Oxford-educated lawyer named Charles Lyell shattered that belief and revolutionized geology.
Lyell spent years traveling the world, studying an overwhelming number of rock formations and fossil samples. He had a brilliant eye for detail, and piece by piece, he began to see that the rocks told a different story. While catastrophes such as volcanoes, earthquakes, and floods occasionally affected the planet, the greatest changes were the result of an incredibly slow and natural geological process, a process driven by wind, water, erosion, and the heating and cooling of the Earth. A record of those changes was contained in the layers of rock. But here was Lyell's most radical insight. The mechanism for that slow process of geological change was time, lots of time. The Earth, Lyell argued, was far older than was generally accepted, and he presented proof of his findings in a landmark book called Principles of Geology. Today, its publication is considered the birth of modern geology. Sam Bowring is a professor of geology at MIT.
I think very important in Lyell's development of thought was a trip to see the volcanoes of Italy, and Vesuvius, I believe, in particular, where he actually saw that the mountain was built up of successive flows, and they had some of these had a good idea of when they were erupted because they were historic, and he was able to use that to extrapolate that the volcano itself must be hundreds of thousands of years old. And at the time, talking about hundreds of thousands of years was revolutionary. Others argued for a directionality in evolution, that the Earth on day one is not the same as the Earth today. Some secular change has occurred, and this is a debate that geologists have today. Were plate tectonics operating 4.5 billion years ago, or is it something that developed later on in Earth history?
Today, many consider Charles Lyell to be the Charles Darwin of geology. In real life, the connection between the two men was significant.
Darwin took the first edition copy of Volume 1 of Lyell's treatise on his cruise with the Beagle. And what he realized from reading this, as he was also simultaneously worrying about evolution, was that here was the solution to evolution. We had limitless time.
Lyell's discovery set off a firestorm of interest in determining the true age of the Earth. Until then, most everyone believed that the planet was young. But with the publication of Lyell's seminal book, geologists wanted to know how young. Our next great discovery provided an answer. Exactly how old was the Earth? The question persisted until 1907, when American chemist Bertram Boltwood discovered a way to make the rocks and minerals of the Earth provide an answer. Scientists already knew that rocks contained naturally occurring radioactive elements, such as uranium. They also knew that each element decayed into other elements, according to its own rate or clock, and that rate almost never changed. While studying these rates of decay, Boltwood found that mineral samples of uranium always contained traces of lead. It was an indication he believed that lead was the last element remaining from uranium's slow process of decay. From this observation, Boltwood put it all together. If he measured the amount of lead contained in a uranium sample and calculated it by the known rate at which uranium decays, he could determine the approximate age of the rock. It was a breakthrough discovery. Suddenly, scientists had an extraordinary and accurate new tool for calibrating the geological history of the Earth. It was called radiometric dating.
The great thing about radiometric dating is that it allows us to determine the age of the rocks in the Grand Canyon with quite a bit of precision. so that we can understand the whole history of deposition of these rocks before the canyon was carved. We know that the rocks in the very deep part of the canyon are 1.7 to 1.8 billion years old, and yet they're overlain by a flat surface of sandstone that's only 530 million years. So without geochronology, we would never know that we're missing more than 1 billion years of history across that surface. Now, other places in the world have that history. Here we don't have that history, and that's the important thing to remember. The geologic record is remarkably incomplete.
So a century ago, geochronology, time in the Earth, a century ago, what was it, an accuracy of 10%, 50%?
100 years ago, we didn't even know what we were dating, so uncertainties were much, much larger. They were getting dates of around 2 billion, which, of course, was a huge breakthrough in terms of understanding how old the Earth was, but it was only half of the true age of the Earth. And it really wasn't until the 1950s that people began to date meteorites that we began to realize that the Earth was probably 4.56 billion years.
To appreciate how much time that is, consider this. If we compare the entire history of the Earth to a span of 24 hours, 1 million years would go by in about 30 minutes, which means that the entire epic story of human civilization would be over in less than 1 second. Not even a tick of the clock. So why is this so important?
When we look at the history of evolution is punctuated by incredible extinction events. The Permo-Triassic extinction 251 million years ago killed 90% of everything that lived in the oceans. So the question is, was this sort of a gradual process where we saw increasing amounts of extinction, and then finally the last hurrah, or was it catastrophic? Was life wonderful on the Permian Earth, and then suddenly everything went extinct? The way to answer that question is through high-precision geochronology. And the data that's accumulating right now suggests that it was an extremely rapid event. So as soon as you say a rapid event, the one model we have that works very well is impact of an asteroid. And recently there has been some evidence put forth that suggests there may have been an asteroid at that boundary impacting the Earth. The other aspect of extinctions that's really important, and to some people even more exciting than understanding the extinction itself, is what happens to the ecosystems. How long do they take to recover? When you wipe everything out, it's like resetting the whole evolutionary clock, and then you allow new things to fill the ecosystems that were completely obliterated. It could be that if it weren't for that extinction, we wouldn't have seen the rise of dinosaurs and then mammals. We could live on a very different planet. We wouldn't live here.
You look at this view and you feel like an insignificant speck.
Right.
And the grandeur of it is astonishing. But then when you think about what you can learn from it, then it's a whole nother level of...
It is. And it's like a book. There's lots of information there waiting for us to extract it, information that we haven't even thought about asking the rock record to produce for us. So there's a lot to do.
Well, that's job security for science.
Yes.
The Earth is a complex and dynamic planet. Crust is shifting, the mantle is moving, the atmosphere is constantly in flux. All the species that live on the Earth are changing along with it. Our ancestors did, or we wouldn't be here. The Earth challenges all living things, and so far, life has been up to the challenge.